Alright, so what can we say about lines? Well, I hope you all are familiar with normal line notation, y equals mx plus b, which is where there are more formulas, but I'll just start with this. So if we have a Cartesian plane with an x and a y, we're able to put any point we want and have a slope with y-intercept b, and this will define a line for us. There are other ways to do this. Equations such as y minus y1 is equal to x minus x1. That's another way to define it, where we just keep it this way and introduce our y value or x value that we want to be the base value, and then we compute x and y. And there's another one where we have 2 points, and oh yeah, I guess x1 and y1 in this case are a point on the Cartesian plane. Otherwise we could have x1, y1 and x2, y2 and form the equation y1 minus y minus y1 over y2 minus y1 is equal to x minus x1, x2 minus x1. Well, I hope we're familiar with gradient, rise over run. So essentially this is how this works is you have y minus y1 over x minus x1 is equal to, if you manipulate things around, then you have y2 minus y1 over x2 minus x1. And then you just have this identical equation because this is m, recall, it's the change in height over the change in x, which will give you the gradient of the line. But the problem with these equations are that we're not giving importance to both x and y, and we're treating them in a very dependent manner in like one equation. So we're going to introduce another form, and this is going to be called parametric equations. Before talking about vectors, we're just going to manipulate these algebraically. So we have a slope in every line. P, we can denote it P over Q, where P is, I guess, rise over run. So that's change in x, change in y, whatever you want to call it. And we would also want to have a point on this, on the plane, just to know where we start from, because given a slope, say we have the slope of 2, we're gonna go 2 units every time we have 1 in normal notation, right? But this is the same thing if this slope is also 2. Ignore like the misrepresentation, but they're meant to be parallel. This slope is also 2, but we need a point so that we can establish where it is on the plane. So that's why a point is important. So we need a point x1, y1. Now our equations are x is equal to x1 plus p times t. Now I should label it q. Run. Dependent on x, y is equal to y1 plus pt. Now we're going to say that p is not equal to, sorry, we're going to say that q is not equal to 0 in this case because, well, if we let q equal 0, we're just going to have a vertical line with an infinite slope. So we don't want that. There's no point of that. Now, this notation is, as you can see, dependent on t. Why it works, you might be curious to why this equation works. Well, think about change in x. If we have a plane, right? Let's say this is 1, this is 1. So how, if we have a line with gradient of 1, right? This is 1. Then any t value, right? As we change it by, so rise and run, like delta y is 1, delta x is 1. So yeah, m is 1. So every time we pick a value, essentially q is our change in x. And this is pretty obvious because I wrote it here. But q's are change in x. So our x always changes by this fixed amount and our y always changes by p, the fixed amount. T will just establish a position where it affects both in the same manner, so it will stay as the same line. If our t wasn't linked up, then these equations have no correlation to each other and would not form the same line as they would with a y equals mx plus b equation. Now that we've defined that, now we can move on to vectors. Now let's have a equation of a line. Let's say x is this variable that stores this equation of a line. We know we want to find an x and y coordinate, right? We're going to look at 2D and we're going to have an x1 and a y1, because this is how we normally represent vectors, right? We plot our x values and then our y values when we're working in R2. And if we go to R3, then we'd probably have a z value. It's like standard notation. Then you want to add your t with your p and q over here. Now what this forms is the basic calculation that we just said, because we have an equation now. It's called a parametric equation. So to get the first parameter, to get this line x, this parameter x, the top part is going to be an equation that gives us this. So x, this is like small x. This is another x. 1 plus pt, and then we have y equal to y1 plus pt, and that's this y over here. So these are called parametric equations. Now, as you might notice, these two are now vectors, and they can have their own variable that defines them. So we can say this is vector v, this is vector w, and they're both in R2. So now to define this, let's suppose that line, we can say x is equal to v plus w times t. Don't forget about the t. That's how our equations work. And obviously t is in the real numbers. And to explain how this builds us a line, well, what basically is happening over here is, say we input t equals 0. This is its starting point of this line. So we've defined a start for this line. So let me show you. If we have an x-axis and y-axis, our vector v, say our vector v is here, it defines the starting point of the line, so when t equals 0. Now what w does, it gives us direction. So say our w is something like this. Now we know to add these two vectors, we can use the parallelogram law, or we can just use the tip to tail addition. And basically that would mean that when you're adding w, we're gonna get this direction that's important, because no matter what t it is, it's going to stay consistent on this line. And this is actually our line x, the thing we define as x. And you might have noticed that these are terminal points of vectors. But why is it a line? Because we're defining the whole set of these. So for any t in R, so by combining all these different points, we basically have a line. And we can also write this line as a set of points, as I just said. So we can say v plus t w, where t is in the real numbers. And we're going to ignore when, let's say w does not equal 0, because in that case, well, we're just going to have a single v, and that's not a line. That's just a vector. And yeah, so w does not equal 0. And there are, basically it's the same idea in Rn. This works in Rn. We just talked about it in R2 because it's simpler for us to conceptualize. But say we have two vectors v and w in Rn. and then we have um, terminal point v for the vector v with a coordinate of some sort, v1, v2, vn. Now this is a coordinate, a vector we're going to note like this, but it's essentially the coordinates are linked except this is a row and this has to be a column. So the terminal point is our starting point, because I'm going to say that v is our vector that defines the starting point when t is equal to 0. So this line we define, well, they both have to be in the same dimension, so the n must remain the same. So w must also have n components, and we're just going to define it the exact same way. It's just x or something is v plus t w. So that's exactly the same thing. And you can generalize the concept of parametric equations as well. So we have n parametric equations because these are x1 is equal to v, sorry, that's not vector, it's an element component, t3w1, x2 is equal to v2 plus tw2. This extends to xn is equal to vn plus twn, which might be useful later on. Now, there's another idea that I can quickly explain, and it's if we're given two vectors or 2 points on the line, say we have a point x on the line and a point y on the line, we can actually find out the equation of the line that it's on. Now, how we would do this, well, remember these are vectors. Our line is defined by vector points, so these are vectors. I'm just gonna draw it out. Let's say x might be here. This is just to conceptualize. Obviously, I'm drawing it in R2, and let's say y is maybe here. Well, if these are both in a line, well, it's obvious that the line has to be here. There's no other line that meets those 2 points. So what is this? Well, this is essentially how we would compute the direction, right? This is our direction vector. This is our w from the other examples. How do we calculate that? Well, that's pretty simple. This is just a normal triangle law that this line, depending on how you want it to go, if you wanted that direction or that direction, it's either x minus y or y minus x. Now you can use either one because we don't care about the direction when we make a line. We might have a different equation, but the line will be the same. We can choose any starting point we want, but the line will be the exact same. Now, another concept, we talked about span in our last tutorial, but how could we use span here, you might think? Because I've defined my line with x. X is equal to v plus tw. How can we span this? Well, to span something, it has to go through the origin for sure. Because by spanning something, every vector starts at the origin. Since we're working with vectors that start in the origin, all our vectors are starting in the origin. The only way for a vector not to start at the origin if it's being transformed in some way. It's moving away, so if we add something here, this is not going to be a line that goes through the origin. It's going to be like this. So that's why it's important to understand what the span can do. So, in what case would it go to the origin? Well, firstly, recall that if v is actually the zero vector, then we can say that the x is just the span of what? X is the span of the w vector, right? But, of course, that's pretty obvious. What other case would it go through the origin? Well, the only case it would go through the origin, apart from v equals the zero vector, is if v is actually some type of scaled vector that is also in the w direction. It's a scalar multiple of the w vector. Because, why must this work? Well, that is because essentially we're gonna have t w plus, sorry, we're gonna change this. It doesn't have to be t, it can be something else. Let's say it's b. I don't think we've used b yet, and b is in the real numbers since it's a scalar multiple, plus t w. Well, in this case, what happens is we can put w on the outside, factor it out. We have b plus t, but b plus t is a real number. So this is a span. This can also be a span. And this works for Rn. This works for any dimension. This works for any R. All these ideas here work for any R. This works for any R. These are parametric equations are in any R. So just keep that in mind, and thank you.